In this video, I introduce semi-supervised real-world learning for feedback-efficient preference reinforcement learning. Preference-based reinforcement learning trains agents to perform targeted tasks with human preference between two agent behaviors without a predefined reward. However, preference-based learning requires a large amount of human feedback, which makes preference-based reinforcement learning methods difficult to apply to various applications. SURF is a semi-supervised real-world learning framework that utilizes a large amount of unlabeled samples with data augmentation. SURF combines semi-supervised real-world learning and data augmentation for feedback efficient preference-based reinforcement learning. Semi-supervised real-world learning leverages unlabeled samples when amount of the labeled samples is limited, while augmentation is improved data efficiency as shown here. This unsupervised real-world learning, this trajectory 0, trajectory 1, which starts from the same initial state, and this cross-entropy is used to train the real-world model. This data augmentation, this is the original segment, and this is the augmented segment. Given a pair of segments, sigma 0 and sigma 1, human gives feedback indicating which segment is preferred, namely y is selected from 0, 1, and 0.5, where y is equal to 1 indicates sigma 1 larger than sigma 0. Y is equal to 0 indicates sigma 0 larger than the sigma 1. And y is equal to 0.5 implies an equally preferred case. Each feedback is stored in dataset D as a triple sigma 0, sigma 1, and y. A preference predictor uses a real-world function R psi caret to model human preference as shown here. This Bradley Terrell model and explained in this figure, which denotes probability of the segment sigma 1 over sigma 0 indicated by the real-world model. The real model is trained by cross-entropy loss through supervised learning with human preference as shown here, without using human labels. Instead, semi-supervised learning and data augmentation are used to improve the feedback efficiency of preference-based reinforcement learning. SURF leverages a large number of unlabeled samples collected from environments by different pseudo-labels. Given a labeled dataset DL, an unlabeled dataset DU is used to train the real-world model R psi together. The pseudo-labels Y caret for unlabeled segment pair sigma U0, sigma U1 are generated by pseudo-labeling approach as shown here and planned here. First, train the real-world model on the labeled dataset. Then predict the labels for the unlabeled dataset with a predefined threshold tau. Finally, use the labeled data and the pseudo-labeled data as a new training dataset to fine-tune the real-world model. By generating pseudo-labels from the prediction model, SURF obtains a free supervision for optimizing real-world model. To fill out inaccurate pseudo-labels, the SURF only uses unlabeled samples for training when the confidence of the predictor is higher than the predefined threshold tau. The real-world model R psi is optimized by minimizing the objective as shown here, where P asterisk is the index of the predefined segment from the pseudo-label. Semi-supervised learning mixes supervised and unsupervised learning. Some of the data are labeled, while usually most of it is unlabeled. Given two segments and human preference, sigma 0, sigma 1, the y, self-generates augmented segments by cropping the subsequence from each segment or origin on in each frame in the segment actually here. This is the original segment, this augmented segment. This original input segment. This uses different operations to get augmented segments. The augmented samples together with the labeled samples are used to fine-tune the real-world model with the cross-entropy loss. The data augmentation assumes a human may keep the relative preference for slighter shift or resize the versions of the original segments so that the data augmentation can improve the model and generalization. For more details, please check with these references. Thank you. Bye.